Recently, I was approached by a company who were quite enthusiastic about Fusion. Honestly, I know the feeling. And they asked if I wanted to give a talk internally about it. I said yes, and the talk went something like this. Hello everyone, I'm Dan, and today I'm going to be diving into some of the internals and thinking behind Fusion. So, just a quick bit about me, a personal favourite topic of mine. I've been on Roblox for 1.5 decades using the LTOP username. I code a lot. I design a lot. I code designs a lot. Yeah, that's about it really. Oh yeah, I like making music too. That's fun. Anyway, this talk, it will be some parts theory, some parts practice. You do need to understand both in order to understand Fusion because it is half coding convention and half actual implementation. But don't worry, I'll keep it simple. No big fancy look at my mathematics PhD words, all just simple stuff. I'll be happy to take questions at the end. I'm sure you guys will have plenty. So let's start easy because I understand some people might not have used Fusion before. What is it? Well, it's the number 2 library used for UI development on Roblox, second only, of course, to React. And the weird thing about Fusion is that, despite being a UI library, it doesn't provide any actual UI, no components, no pre-made templates, nothing like that. Instead, it's all about the workflow of building UI. Here's about addressing problems that often come up during UI development, particularly around the management of dynamically changing state. Really, it started with a simple observation. It's hard to follow changes to dynamic state. You see, Luau has no native method for listening to variable changes. Instead, there's only really 2 ways to do it without a dedicated API. You could poll the value, just checking it in a tight loop, but that sucks, and everyone here knows it sucks, so we won't even talk about that. You could also hard code some function calls next to wherever you're changing the variable. But that also sucks because it strongly couples your code together and it's easy to forget or accidentally break it. Everything sucks. But why? Let's be productive about this. What do we want our code to look like? Could we imagine something better? Well, let's try. Ultimately, we want our code to respond to dynamic data sources. So what we'll end up doing is designing a nice API for dealing with data sources. Firstly, we're going to need to hide the state of the data source behind some kind of opaque state object. We don't want people randomly mutating the data and overwriting it, but we still want to be able to refer to the data. Then we can provide a standard way to read the value of the state object and a standard way to observe changes to the state object. That's enough to give us a nice workable interface that doesn't couple our code too strongly. Fusion provides a few standardized implementations of this state object interface. All of them share that same common interface for reading and observing changes. The differences are where they get their data from. So let's start with value objects. These are state objects that just directly store a value. They include an extra set method which you can call to change the value, and this isn't technically uncontrolled mutation since we're going through the object every time, but it's kind of close enough that it should be pretty simple and familiar in actual practical usage. You can basically just use it like a variable. Where things get a little more useful and interesting are with computed objects. These aren't settable. Instead, they run a single predefined computation to decide their value. As the computation runs, it'll collect any used state objects via that use callback. The computed object then keeps track of them somewhere, and if any of them changes, the entire computation is rerun. This is super useful. So there's even extra variants designed for things like processing values inside of arrays and tables and stuff like that. As a final example of something more dynamic, Spring and tween objects are state objects that smooth out changes over time. You give them some state object to follow and they'll animate towards that goal state. If it's a spring, then it'll use a physics simulation, or if it's a tween, then it'll use some kind of easing curve that you give it. These are super useful for animations, transitions, that sort of thing. Hopefully you can see that it's very easy to chain together state objects to form entire calculations. At any point, you can read or observe changes to any value in the chain, and all the changes just naturally flow down. This takes a lot of pressure off of developers so that you can focus on your logic, not your logistics. Let's elaborate on that. In what ways does this take pressure off of developers? What guarantees and assertions can they make? Let's start with our first guarantee: no missed changes. Think about it. State objects are completely opaque, so only they can directly write to their dynamic state. Therefore, the state object must know every change that occurs, because it's the one doing every change that occurs. Therefore, it can always propagate the knowledge of those changes to every one of its users every single time. Or at least that's about 99% true. There are some weird ways you can get around that, but that broadly doesn't matter if your code is reasonably hygienic. Just don't do any uncontrolled table mutation or garbage collection wizardry. Anyway, let's make another guarantee. No surprising results. Again, state objects take away your power to write freely. That means they only change in ways that they are programmed to do. For example, if you want to change a computed object, you have to return the new value from inside the computation. There is no other way to set the value. That means you can rather easily audit any result that you get just by following the whole process in reverse. Because of this setup, there is always one definite order of events, and in the case of computed objects, all of the cases have to have been explicitly written out, because if it's not in the computation, it can't influence the computed object. The third guarantee is that there are no subtle failures. That is because Fusion provides the implementations of these state objects. These implementations handle almost all of the difficult, finicky processes on the developer's behalf, ensuring things execute at the right time, in the right order, in the right way, blah 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 blah. To that end, they have been extensively tested ahead of time so that they can be trusted to work properly. That leaves the developer with the easy stuff. That is to say, your code is designed to have nearly zero subtle failure cases. So, this is great. Our code now behaves totally predictably, it's nice and loosely coupled, and it is very pleasant to debug and extend. But take a look at this. This code is a ticking time bomb. Consider this sequence of events. If you recompute tautology after smaller, but before larger, then you will see that smaller is larger than larger. Congratulations, you just broke mathematics. So, what went wrong? The problem was that we compared the newer smaller to the older larger, so these values were coming from two different points in time, and they were inconsistent with each other. This doesn't make sense, and it's going to confuse your users, and it's going to cause tons of bugs. We expect our calculations to run on data from the same point in time. That leads us to our golden rule then. Don't update something until you've updated what it uses. Basically, this means we can't use callbacks or events. They tend to run away with updates. You could imagine how each callback might then invoke other callbacks, and so on and so on and so on. We just lose control. So instead, we will manually store the connections between our state objects, so that we can sort through the whole structure using some kind of algorithm. This algorithm should return things in topological order. That is, things an object uses should appear before the object itself. It's what we just discussed. To that end, I invented the sets algorithm to solve this elegantly and efficiently. At least, I think I invented it. I didn't find anything like it online after a lot of research, but I wouldn't be surprised if someone else had the idea. I first published this technique to my blog, Technical Fluff. I'll provide a link afterwards if you're interested in the full write-up. So, let's start with any old structure. There can be multiple different ways to get to each object. These are the ways or routes that updates will take when they propagate through the system. If we were using events or callbacks, our updates would flow down all of these routes at the same time and cause mayhem. To avoid that, we only want to update objects after everything behind them. So we're going to need to exhaust every possible route before updating the object. Let's start from the top of the structure and flow down through every single route. As we arrive at each object, we will add 1 to a counter at that object. When you're done, you know how many routes will flow into each object. Now we can just do that in reverse. As we arrive at each object, we will take away 1 from each counter. Only when we've exhausted every other route going into a given object will that counter hit 0. That tells us it's safe to update the object. Once you've explored all of the routes and updated all of the objects, you are done. Let's go for a bonus round. During this process, we might update an object and it'll recalculate and do its magic, but then it'll just spit out the same result that it had before. That's clearly not going to change anything downstream, so why bother recomputing all of that stuff? We can fix this rather easily. To start, we need a needs recompute flag per object. When we set the flag, it indicates this thing needs to be recomputed. Pretty simple, hopefully. Then we could just go down the structure as usual, For each object, we will only actually recompute it if that flag is set. Of course, we still need to count down and exhaust the roots. This is just about the actual recomputation. If, after recomputation, that value changes, then we just set the flag on all of the objects that are connected. And et voila! We can skip even more updates and waste even less CPU time. Alright, nerdy graph theory stuff over. TLDR. Store the connections between your state objects, figure out all the routes you can take, then wait until you've exhausted all the previous routes. Finally, just recompute so long as one of your ancestors actually changed value. Seems pretty simple. So that's the brief version of that algorithm. If you want a proper recap or some more details, you can visit the original blog post at that link on the slide. I'll just hang here for a couple of seconds in case anyone wants that link. I know, it's a riveting slide. Very, very interesting. Definitely worth hanging out on. Love that font choice. Alright, let's just move on before this gets weird. With all of that context behind us, let's revisit something specific we glossed over earlier. This is the code pattern you use in Fusion when you want to observe changes on a state object, but it might look a bit verbose to you. You might ask, why not implement that onChange method directly on all of the state objects? Well, the main problem is that would be a lot of redundant duplicate code. Every single state object would have to accept and store callbacks, then run through that list and call them in the exact same way whenever they get updated. But remember, we just made a structure for updates to flow down through. Let's utilize it. We can feed the updates into dedicated observer objects, which can store and invoke the callbacks on our behalf. So we don't have to write our own custom objects to receive updates, and we don't have to repeat the same logic everywhere that we want to listen for updates. So let's take another look. This time I've separated out the object creation. When we create the observer object, we internally connect it to the state object that is going to observe. This means that updates will flow down into the observer object. Then we register a callback with the observer object via onChange, which saves the callback to a list internal to the observer object. Finally, when that observer receives an update from its connections, it will call all of the callbacks in that internal list, which means our code runs. Simple and reusable, even if a bit unconventional. So great! We've explored how to properly update things in the right order, we can skip over redundant recomputations, and we've figured out how to create a lovely unified system for registering callbacks and managing observation logic. But we just played ourselves. There is just one small tiny problem with our object structure. It's nothing much really, just it will live in memory forever. You see, every object is now connected to each other, so no objects can garbage collect until every single state object we have ever used becomes completely inaccessible, which will probably never happen. The intuitive solution to reach for here, at least if you know metatables, is to use weak metatables. Our state objects should definitely strongly connect to what they depend on because they would break if those were garbage collected. But they should weakly connect to what they don't depend on because that wouldn't affect its proper functioning. As we will soon discover, it certainly kind of works. The first problem we run into is that observer objects get garbage collected. You see, users expect to receive updates when they manually disconnect their callback, even when the observer object is no longer accessible. It turns out a lot of scripts just connect to stuff and exit their made code chunk, leaving only the callbacks to respond to incoming data. Okay, we can just strongly reference the observer somewhere temporarily, just while it has an active callback. Problem number 2. Observer objects don't get garbage collected. In direct contradiction to my last point, users expect things to get garbage collected when they're done with them. But now observers live forever until they're disconnected, so... Remind devs to clean up after themselves? This is getting sticky, and that's not even before we mention problem number 3. No finalization code. For some pretty good reasons, Luau disables the GC meta method, and while that might be good for Luau, that's terrible for us. We have no way to clean up the data in our objects when they get garbage collected. I mean, we need to destroy instances and disconnect events and clear variables. That is, it's impossible unless you poll to see when it gets garbage collected. That's not great. Problem, you get the picture. Let's just admit this is probably a terrible idea. This isn't going to work, honey. We flirted for a bit. Even looked like it was going to be great. But we're breaking up. Okay, Let's try a different solution. Manually freeing up memory. We'll just tell the users to destroy things themselves. It isn't pretty, but at least it's reliable. It doesn't have any overhead, and we know it can support whatever we need it to. As long as the user actually calls it. Users aren't good at cleaning up after themselves. They didn't invent Rust for nothing, right? So, okay, let's try and tackle that problem. We need some sort of memory management convention, something that guides the user towards cleaning things up at the right time without having to think too much about it. Maids are a good start. I mean, James, great guy, Quenty, wonderful, but it's just bulky, object-oriented programming overhead. We don't really need that. Cleanup tables are simpler. Just add all of your stuff to a table as you make it, then destroy all the contents later by passing it into a method. No objects, no overhead. Unfortunately though, both methods fall short in one key area. They still bloat line length with repeated code that's easy to just mess up. We really want something the user can just forget about almost completely. So let's broaden our scope. How do other programming languages deal with similar problems around freeing up memory? Well, there's arena allocation or region inference, but well, they don't really help out with the developer experience so much as they solve a technical problem well. There's my personal favourite, Rust-style ownership and borrowing, but that's a bit harder to pull off in Luau. It wasn't really designed for ownership concepts. And of course, there's garbage collection, and we know what the issues are with that approach already. So, what's the solution? No, seriously, what's the solution? This is an open question, because as it so often turns out, memory management is kind of hard. We knew it back when computers were unwieldy, and we keep reinventing the problem to this day. I think it's safe to say we're working on this one, but maybe it's appreciable while it's perhaps a little less than optimal right now. We're tidying things over with a mix of the garbage collection techniques, but we'll probably have to change direction. Let's change the subject. Okay. Throughout this whole talk, there has been a massive elephant in the room. I haven't mentioned instances once. The reason? It turns out some elephants just aren't all that interesting. You'd be forgiven for thinking that instance management was more integral to Fusion. It takes up a majority of screen space in most code bases. But the boring reality is that there's no fancy tech at all here. We already did the legwork. It's just pretty syntax for observer objects, pretty much. We're just observing state objects and writing to whatever property needs to be written to. There are at least a couple of nuances worth mentioning though. With instances, you generally have to be careful what order you do things in. It's not that you'll break something, chances are it will always look correct eventually, but you'll end up doing a huge amount of wasteful work if you're not careful. I hope you're reading that code snippet and getting some serious anxiety from that order of events. Generally, the correct order of events is firstly to modify yourself, then modify your children, then modify your ancestry, and finally observe your events. I hope this slide soothed your nerves a bit after the horror show that was on the other slide, so we need to do this. By the way, just to remind you, this is how users are specifying properties in our system. They're passing in a table of them all at once, and as it just so happens, those properties will not be iterated over in any defined order. It may as well be random. As it turns out, a lot of libraries and frameworks don't actually do anything about this. At most, I've seen them defer setting the parent, but it seems like an oversight. Fusion's solution to this is to sort the work into 4 buckets. The self bucket for modifying the instance itself, the descendants bucket for modifying the children of the instance, the ancestor bucket for modifying the ancestry of the instance, and the observer bucket for observing changes to the instance, for example, connecting to instance events. This broadly lines up with the order of events that most developers already know to implement in their own handwritten code. All that's left then is to process each bucket in order, one at a time. Alright, cool, so now let's talk about the one special bit of technology that was built for instances. Sometimes we're not just assigning properties, but we're doing other more arbitrary work on the instance. You've heard me talk about assigning children and connecting to instance events. But how do you actually do that? The answer is to use these special keys in your property table. Instead of just being strings like any other property, these are objects that you use as keys. You can tell when one's being used because you'll see the square brackets being used to pass the object as a key. There's a few good things about using objects for these special things. Firstly, they'll never conflict with the string keys that are being used for property assignment, so we don't have to worry about Roblox introducing new property names in the future. It also keeps all of our instance information organized in one table, unlike other frameworks that choose to create dedicated tables for things like assigning children. Furthermore, these special key objects can carry their own functionality, which means third-party libraries can make their own special keys without having to hack into Fusion. To see how these objects carry their own functionality, here's the type signature for special key. You can pass any object of this type as a key in between the square brackets, and it will be understood by Fusion's instance stuff. The first two fields aren't too interesting, they're just type information, so Fusion can check the types of your objects and maybe print out some useful debug information. The stage field specifies what bucket of work the special key should get dropped into, and therefore it determines what stage the special key will run at. And finally, it specifies an apply method, which is called when it's time to execute that bucket of work. It receives the instance and the value passed in via the property table, but it also conveniently gets a cleanup table in case it wants to run any code when the instance is destroyed. The great thing about special keys is that you can do almost anything with them. Of course, you have your usual children assignments and event handling, whatever, which should be familiar to React users already, but we even provide facilities for creating live updating state objects from properties, or nicer syntax sugar for cleaning up stuff alongside the instance, or even just recently, setting and observing attributes and tags. And the best part? Anyone can extend the system, even you, perhaps even just for a one-off thing. Fusion does not have to officially support anything, so there's no long process or pull requesting to get juicy new features. Right, so if you haven't fallen asleep yet, congratulations, you've made it through the meat of this talk alive. Take a deep breath, loosen up a bit, we're done talking about the internals. Quite literally done, by the way, there's literally nothing else internal to talk about. From here on out, we're venturing outwards into the wild west of coding conventions, ecosystems, and usage patterns. Let's talk a little bit about Fusion at scale. You see, it has different scaling characteristics compared to something like React. React is best optimized for changing instances in bulk, because it stores a lot of data about them and performs big comparison operations to check whether they're up to date. On the other hand, Fusion is better optimized for short, random update paths. That is, it does a better job of updating simple things frequently, which is why you don't have to jump through any hoops to do things like animation, for example. I'm going to inject a touch of original thought here, and I'll assert that Fusion's best case is more realistic than React's best case, because most updates are not bulk updates, and if you do have bulk updates, they're usually avoidable pretty easily. It turns out that a lot of updates are just things like hovering over buttons, or a counter ticking upwards, or perhaps just a loading animation. When looking at how Fusion works at scale, Lua Learning is a great case study. Now, I'll let Zach keep all the details to himself, I don't want to disclose anything outside of my purview, so I'll just keep things simple. Lua Learning really is just the worst case scenario for Fusion in a realistic setting. Almost all content in-game is user-generated in real time, or connected to Zach's LiveOps system to be updated at, I don't know, any hour of the day. The UI is incredibly dense, with hundreds of possible micro-interactions, and all of that has to run anywhere, including on some very low-end phones. Oh, God. But they do have these really cool 3D quest boards. They're very... Okay, I might be a bit biased, but okay, seriously, they're really cool. Anyway, where most UI frameworks might start feeling the heat, Fusion wipes the floor clean. It doesn't miss a beat, largely because Fusion is just so simple. The best way to gain performance is just to do less, and Fusion does about the bare minimum of work that it has to. What's that? Oh, Zach, yeah. I mean, I don't know how you're phoning me, I don't have anything in my ear, but you just said you issued a correction. If you use an FPS unlocker, you get like 8,000 FPS, something? Okay. Nice talking to you. Okay, bye. Of course though, performance is about more than just frames per second. We also need to take a look at memory usage. Now, let's be 100% honest here. Fusion in Lua Learning is almost certainly not as optimal as React when it comes to memory usage, simply because Lua Learning has so much dynamic state to hold in that React would not have to hold in just because of React's specific model. And yet, even with that factor, it turns out that memory is tightly managed anyway, because the vast majority of objects in Fusion are built upfront, and very few are required on top of that. In addition, since I spent a lot of time working on Fusion's garbage collection, it all actually works properly, so memory leaks are kept to an absolute minimum. This is in contrast to many other UI systems, even Roblox's own core scripts, yes, shots fired, where issues like long-lived event connections can cause a gradual memory usage buildup. So I think it's safe to say that, even at scale, Fusion has a very stable memory usage, thanks to a lot of careful work. While we're around the topic of usage at scale, we should also talk about modularity. We've already established that Fusion encourages loose coupling for state objects, but what about loose coupling for UI instances? It turns out it's easier than you think, and it's all thanks to some smart API choices that we made earlier. Because Fusion's whole instance layer is not much more than a light wrapper around instance.new and some server objects, Fusion inherits the same great reuse patterns that you would see with handcrafted code. If you want to reuse a button, then you just make a function that constructs buttons and you're off to the races. By convention, these functions take a simple props argument, which is a table of properties, similar to what you saw earlier. Notice there's no special component class here, and yet we didn't have to do any special handling of anything. When we create our instances, Fusion will handle the differences between state objects and constant values for us, which means we can pass properties through transparency. Any created instances are returned directly, so we can slot in our components anywhere we could otherwise have built the instances ourselves, including in property and child assignments or even nested inside other components. And ultimately, this means components are completely ephemeral. Since components are just function calls, they need no trace of their existence in their final output, which makes them a zero-cost abstraction. That's pretty nice. And of course, none of this stuff is at any detriment to the developer experience. With even just this small amount of flexibility, you can recreate the power of a domain-specific language, just so long as you have enough components to express the higher-level concepts that you envision. This is a real snippet of Fusion code that exists today in one of my codebases. You can barely even tell that it's Roblox. Finally, let's talk about ecosystem. Fusion is still very, very young, so this is a developing story, but already we've seen some prominent usage of projects like HorseCat for Storybook-esque UI testing and hot reloading, Codify for automatically generating Fusion code files based on UIs built in Roblox Studio, Stylua now supports Fusion-style function call syntax in its automatic code formatting tools, and we have even seen some smaller projects dedicated entirely to Fusion, such as Hydrogen and Tritium. There is definitely still more to do on this front though, and in particular we don't have fantastic support for inspecting state objects yet, nor do we have more modern niceties that integrate deeply with Fusion, such as stateful hot reloading. Though I can at least tease, I have been working on such tools myself. I don't have working prototypes today, unfortunately, but I do intend to run with these ideas in the future. No guarantees though, but I think it'll be pretty cool. So let's just summarize this glorious mess then. UI is kind of hard, and Fusion at least helps by doing a lot of the heavy lifting to take the pressure off of developers. There are all sorts of open questions and loose ends, but we are coming up with good answers right now. Thank you very much, and I am happy to answer any questions you might have. And this is the point where everyone rushes to the comments section.